Morning, everyone, and welcome to the session before last in terms of problem solving. We're doing chapter 35, and we still only have chapter 36 in this class. I have a few problems from this chapter. I have problem 1, 3, 6, 9, 13, and 20, covering basically the different aspects of double slit experiment. Basically, the idea is finding the dark fringes, finding the bright fringes, finding the intensity of the light depending on where we are on the screen and things like that. So those are typical problems when it comes to a double slit experiment. So we're going to cover that. We may do problem 32, and that has to do with the LIGO experiment. So we'll see, because that's also actually an interferometer similar to Michelson and Morley. So we'll see that, and that's probably the main things in terms of this chapter. Then we still have chapter 36, which we're going to start on Monday. Chapter 36 has a couple of ideas actually in it too, and both of them have to do also with the interference and how you're going to make up interference out of only a single slit. So that's what the diffraction is. And then we're going to derive an expression for the intensity of the single slit. The derivation, there are basically two textbook methods for finding it. One of them is using the phasors method, which may not be 100% obvious because it requires that the wave that comes from the single slit need to be broken down into several sources, several points, basically, using Huygens principle. But the point with it is, it's sometimes very hard to construct and actually see the result, okay? There is another method, which is also a textbook method, and that's used by Feynman and a lot of other people too, and that is using complex numbers. Complex numbers will yield the result quickly, okay? That is usually typically what's going on with complex numbers, and that's their power in physics and engineering in general. They're so much powerful that they make any sometimes hard problems, as long as they are linear, into an easier problem to solve. That is really the power of complex numbers. I know probably some of my students at this point in their engineering classes or physics class, they're a little bit hesitant about them, but we need to remember that there are parts in physics, especially in engineering also, when you have to take physics 4D, for example, that can only be done with complex numbers. And I'm thinking in terms of quantum mechanics, the fundamental law, similar to F equals to ma, which is Schrodinger's equation, is a complex equation. The first thing in it is the I itself. So having said that, I am probably more leaning to use complex numbers to show the result immediately. And then probably we're going to use a geometry to see how we can interpret that for the intensity of diffraction coming from a single slit. That's going to be the last proof that we're going to have in this class. After that, we're going to do applications. Now, here is the trouble with that. We are probably going to be finishing the course by the 24th of this month, because this coming Monday is the 17th. That is chapter 36. Maybe at best, we're going to finish its touches by Wednesday of the same week, which is the 19th. Then after that, we would have done plenty of applications, hopefully by Wednesday. If not, worst case scenario, we're going to be finishing them by Monday, the 24th. So there is a possibility that the midterm, the second midterm, or the exam is going to be online, is going to be either the 26th, which is the Wednesday immediately following that Monday, or the 2nd of June. And the reason why I'm saying the 2nd of June is because there is no class on the 31st of May. That's a holiday, actually. So the 31st is a holiday. We cannot do anything on that day. So the only two possibilities for exam two, which is the second midterm, actually covering the second half of the course, is going to be either the 26th of May or the 2nd of June. So that is basically how we're going to do it. And we will see if we're ready for the 26th. If not, we're going to push it for the 2nd of June, which is going to be the Wednesday. Of course, we're on Wednesday. Next Wednesday is not, so that's the 19th. The Wednesday after that, that's the 26th. So that is a possibility. Or the Wednesday after that, the week after that, for the second term. And then we're going to be due for the final, which is scheduled for June 7th, which is a Monday. So that's how the course is laying out right now. Okay, that's where we are right now and everything. So before we get there, we need to do some problems. So let's talk on page 1179, and that's probably chapter 35. So let's get some problems in the way. So let me share the screen. Bring this closer in here. And so the problems that we're going to be discussing are problem, again, 1, because we want to really hammer the ideas behind it. That's why I started with these small problems. 3, and then problem 6, problem 9, problem 13, and problem 20. Depending, we may even do problem 32 on the LIGO, or problem 52, 54, I'm sorry. No, I'm sorry, what am I talking about? 34, not 54, 34 problem, 54 problem. Okay. Okay, so let's get going with these problems in here. So problem 1. So problem 1, although I started with it and it may seem like, okay, it's kind of a, but it has, remember, the problems in here are ranked. They have 3-dot basically system. The hardest problems have 3 dots, and the easiest problem have 1 dot. This is actually a 2-dot problem, so this is not straightforward. Actually, I mean, it's not really that hard, but it's not that easy either. So problem 1, okay. So problem 1, it says a radio transmitting station. So when they say that, that means we are dealing with light. Although probably the frequency is not in the range of visible light, but it's a radio wave. Again, from this idea is coming from chapter 32, okay, where the electromagnetic wave spectrum has the visible light in this range. So this is the red, and this is the violet, and all the colors of the spectrum that we see are in here, in that range. On this side in here, you have the infrared, followed by the microwave region, and then the radio wave. So the radio wave is actually a very long zone, radio waves. So it's somewhere in here. This is for telecommunications usually, okay? For cell phones and signals, sending signals, receiving signals, you use big antennas. So they are usually, the wavelengths are some few millimeters all the way to several meters sometimes, okay? These are very long wavelengths. And then you have shorter wavelengths on the other side. You have the UV region, you have the X-ray, and you have the gamma ray. So these are super high energy wavelengths with super short wavelengths with super high energy, I should say, very powerful, I mean, very big values for the frequency. These lines in here are not really to be taken that they're exactly somewhere a boundary in here where you transition from one to the other. It's kind of they overlap. There is an overlap between these regions. As a matter of fact, depending on the person, there are some people who have problems with vision, that their spectrum probably is narrower than what, I mean, their vision sight is narrower than this band. So again, the boundaries are not exactly, there is no point on the EM spectrum from chapter 32 that you can tell that this is where this whole thing is. The moral of the story is the wavelength is somewhere in here, okay, from this problem. So it says a radio transmitting station operating at the frequency, as a matter of fact, they gave us the frequency F to be 120 megahertz. Megahertz is 10 to the power 6 hertz. Okay. From chapter 32 also, there is a dispersion law, which I mentioned already in chapter 34 or chapter 35 when we talked about it, that says the speed of light is the wavelength times the frequency, where the speed of light is basically a fixed number, which is equal to 300 million meters per second, or 3 times 10 to the power 8 meter per second. So we know what that number is. From here, we should be able to find the wavelength. So if we ever need the wavelength, and every time we're dealing with a double slit experiment or a single slit experiment or interferences, usually we need the wavelength. So this is almost like a given. But just to give you an idea how long this wavelength is, even if they don't ask the question, we should be able to find what this wavelength is. It's 3 times 10 to the power 8 divided by this number, which is 120 times 10 to the power 6. This one and this one cancel. I'm left with 2, which cancels to these 2 zeros. So the wavelength is 3 divided by 1.2, which is few meters. As I said before, the telecommunications in this range in here can be of some meters. 3 divided by 1.2 meters, 1.2, 3 divided by 1.2, divided by 1.2, that's 2.5 meters, okay? So this is 1 meter. So it's twice as much, basically. Slightly, if a person stands and pull his hand up or her hands up, that is about the wavelength from the extent of the hand all the way to the feet, basically, to his feet or her feet. Okay, so that is the length of this slightly less than the ceiling, okay, which is about 3 meters high. Okay, so this is roughly the numbers that this is the telecommunication tower, how much frequency it's sending in here. Okay, has 2 antennas, 2 identical antennas that radiate in phase. Antenna B is 9 meters to the right of antenna A. So we need to draw this. As we're reading the problem, we really have to draw things to see what's going on. So we have 2 antennas. We have antenna A and antenna B. Antenna B is, so we have to have antenna A first. Here is antenna A. And then antenna B is 9 meters to the right. So this distance in here is 9 meters between them, the separation between the 2 antennas. They are both transmitting this signal of wavelength 2.5 meters and frequency 120 hertz. So remember, omega, the angular frequency, is equal to 2 pi f. So I could do the math in here and find how much omega in radians per second by multiplying 120 by 2 pi. 120 times 2 pi is 753.98 or 754. So this number actually is 7.54 times 10 to the power 8 radians per second. Now this is an omega, okay? 7.54 times 10. Now also we need the K. Remember, probably we'll need the K. I'm not saying that it's 2 pi over lambda. And we have already a lambda, so this is 2 pi over 2.5 meters. So it's going to be 2 pi divided by 2.5. I'm just trying to test something in here so that you guys have an understanding exactly of what came out of chapter 32. So so this is about 2.51. 1 over meter, the unit for K, it's the inverse of a wavelength. If the wavelength is in meters, this is actually 1 over wavelength, or radians over a meter, if you like, okay? The point being in here is the wave look like this. It's actually a cosine or a sine of some K, which is this number, 2.51. If I call the distance between them as X, in here, because we're going to be on this axis in here. So it's x minus omega, which is this number, 7.54, 10 to the power 8, and again, t. So this is how the wave look like, plus probably a phase in here, okay? Plus some phase inside the argument of the plus in here, okay? Some phase in there, which they may be out of phase, okay? That is really how someone is sending a signal with this one, the other one is sending it with the same frequency, the same wave number, except that it's coming with probably a shift in phase, because depending on how far we are from them, one signal could arrive first and the second signal will come later, and they may be out of phase. They may not necessarily be in sync, okay? They will be in sync if they are completely, in this case, there will be constructive interference. So whatever intensity is in front of the first is going to be doubled, that's all. But because they have the same intensity, so both of them, if you add them up, they will be. If they are out of phase, 100% and 180 degrees out of phase, then they will cancel regardless of what's going on. It's going to be zero. That is destructive interference. Now, if the phase is anywhere in between 0 and 180 degrees, so they will add up to some value, which is somewhere in between these two, okay, to these two extremes. But let's consider a point P between the antenna and along the line between the antennas. So we have a point P in here, and it's on the same line between them, okay? Consider a point P between the antennas and along the line connecting them. A horizontal distance x to the right of antenna A. So this distance is x. Okay. For what value of x will constructive interference occur at point P? So point P, there will be constructive interference, is the phase difference between them will be exactly 0 or lambda or 2 lambdas or some multiples of that value. If it is smack in the middle, it's going to be 0 because they will travel the same distance. If it's 4.5 meters between them, that's going to be actually constructive interference. But is there only one of them or more? That's what we need to find. So if it's any time multiples of lambda, it's going to be constructive interference. So let's see now how far this distance is. Obviously, this distance is going to be 9 minus x. And this distance is x. So the difference in path between them, the difference in path, one of them travels a distance r1, which is equal to x, and the other one travels a distance which is equal to 9 minus x. So r2 minus r1, which is in absolute value, which is the difference in both of them, is going to be equal to 9 minus x minus x. So it's going to be 9 minus 2x. This is how much difference in path between the two of them. One of them travels a distance 9 minus x, and the other one travels a distance that is x. And the difference in path, remember when we did the double slit, some of them where R2 is bigger than R1, like this one, or R1 is bigger than R2 and below. So that's why I'm taking the absolute value, because I could be on one side where light will travel shorter from B and longer from A, or it could be on this side, like I drew it in the picture, where light actually from A is shorter, travels a shorter distance than light from B. So that's why I have to take it in absolute value to find all the different possibilities. Now, the phase difference, if you guys remember, when we did the math for it, was the wave number times delta divided by 2. That is actually the whole difference that we made the argument for it from chapter 35. So this is the actual phase difference. When I added the 2, remember, and I said that the omega t cancels the omega t, so I will be left with because it's a wave that travels a distance k times r1 plus k minus k times r2. Obviously, I took r2 greater than r1. That's why I rearranged the expression. I did y2 plus y1, because then it allowed me to do the difference r2 minus r1, because I was looking all along for this scenario, the top one, And that would not really have mattered at all because of the fact that I'm dealing with a cosine. So cosine of what we ended up with, R2 minus R1 over 2, is the same thing as cos of k times R1 minus R2 divided by 2, because of the fact that the cosine is actually an even function. Cosine of alpha is the same as cosine of negative alpha. And that is the point in here I'm trying to say in here. Whether you're looking for points on top or the points on bottom, there is a symmetry with respect to the central point in here. There is a perfect symmetry. And that is coming from the properties of the cosine, actually, when it comes to this argument. So delta in here need to be taken in absolute value, and it's going to account for everything, positive and negative. So this one, as a matter of fact, is equal to different values in here. To have constructive interference, this has to be multiple of lambda, where m can be 0 if you are smack in the middle, or plus or minus 1, or plus or minus 2, or plus or minus 3. So m is a number of the z space, which is the integers, positive and negative in this case. Okay. Having said that, now we can find the condition on the difference between them. Remember, the distance is 9 minus 2x. X cannot be greater than 9 anyway. As a matter of fact, this number has to be always taken in absolute value also because of the fact that it could be negative. So we really have to take that into our absolute value. Okay. If we say that, then we're in business. But we took care of the absolute value by just making m equals to positive or negative. So here is the deal. Then from this expression, delta is equal to 2 times lambda over k times m. But I just know what the ratio of lambda over k from this condition. Do I have lambda over k? Okay. Wait a minute. Oh, no. This already taken care of this. I'm sorry. There is a problem in here in my analysis in here. It's not m lambda. Delta itself has to be m lambda. Okay. The difference in path has to be m lambda. This is the phase itself has to be actually multiple of pi. Okay. This has to be m pi. Okay. That is basically the whole argument with it. It has to be m pi in this case, okay? So this is the phase difference. Sorry, let me correct this statement in here. It's wrong. Sorry about that. Okay. The path difference, in other words, if one of them travels a distance r1, the other one travels a distance r2, the difference between R1 and R2 has to be multiple of lambda. Okay, that is the argument that we made from this class. This is wrong, okay? So in this case, and I know when we square it, it's going to be, whether it's positive or negative, it's going to be always positive. So at the end, it doesn't matter positive, plus or minus, so it's going, that's the whole argument for it. So now delta itself has to be m lambda. Okay, and now this could be 0, or it could be plus or minus 1, or plus or minus 2, and so on and so forth. So delta is 9 minus 2x. So 9 minus 2x must be equal to either 0 lambda, or 1 lambda, or minus lambda, or 2 lambda, and minus lambda, and so on and so forth. That is the argument for it. So again, when the difference is 0, that means 9 minus 2x is equal to 0, and this gives me x is equal to 4.5 meters. That is exactly the condition for a constructive interference, because if I am smack in the middle, both of them travel the same distance and they will arrive at the same point in here at this in phase. So that is condition number 1. How about plus lambda or minus lambda? So I have 9 minus 2x. Remember, lambda was equal to 2.5 meters. Lambda was equal to 2.5 meters. So is equal to either 2.5 meters or minus 2.5 meters. So that's the second condition in here. So I have, in this case, 2x is equal to 9, either plus 2.5 or minus 2.5. So in here, I have two solutions. When I add 2.5, it's going to be 11.5 divided by 2. So, no, let me solve it. So x is equal to either 11.5 divided by 2 or 9 minus 2.5, which is 6.5 divided by 2. Obviously, this one is and we have to keep it in between them. So it's going to be 11.5 divided by 2. So it's going to be 5.75 meters from A, or 6.5, which is 6.5 divided by 2, which is what? 3.25? Yeah, 3.25 meters. Again, we are still within this range, okay? We are either in the middle, 4.5 from A, or 3.25 from A, or what is the other number? 5.75, or almost 6 meters from it. So we're still within this range. So that gives me also constructive interference. The other solution is 9 minus 2x is equal to either plus or minus 2 times 2.5, which is 5 meters. Okay, this gives me x equals to, again, when I move this one to the other side and divide by 2, you're going to give me 5 plus 9, which is 14 divided by 2, that's 7 meters, or 9 minus 5, which is 4 divided by 2, which is 2 meters. Okay, so if we are 2 meters from A, or 7 meters from A, which is 2 meters from B, basically. Okay, that is also constructive interference. Let's see here if we have a solution for 3 lambda. Let's see what's going to happen in here. For x equals to 3 lambda, then we have 9 is equal to 2x is equal to 3 times 2.5, which is just 7.5 meters. And that gives me a condition that x is equal to 9 plus 7.5, that is 16.5 divided by 2. And 16.5 is 8.25, actually. And 9 minus 7.5, and that is 1.5 divided by 2, and that is 75 centimeters, basically. So if we are 75 centimeters, then we have also constructive interference, and we are very close from the other one, which is 8.25. We are 75 centimeters from B. That also gives me constructive interference. I think that's it. Let's see here if we can get anything out of the condition for lambda, for m equals to 4. If m equals to 4, then in this case, we're going to have 4 times 2.5, and that is going to be 10 meters. So, and that is going to throw us completely outside. So n minus 10 is equal to plus or minus 10 meters. And that is going to give me x, which is equal to, with a positive sign, it's going to be 9 minus 10, which is negative 1, divided by 2. And that is going to be negative 50 centimeters on the other side. And remember, the condition said that they have to be in between. So this is rejected. And let's see with the plus. 9 plus 10 is 19. 19 divided by 2. And that is 9.5 centimeters. And that 2 is outside of the other side of it. So this is not accepted. So there are only these points in here, and they are. So x can be 0.75 centimeters from A. This is from A, yeah? All of these distances are in meters. So the next value is 2 meters. The third value is 3.25 meters. And the fourth value is smack in the middle, which was the first condition. And then after that comes the next value from this one, which is 5.75. And then 7. And finally 8.25. So those are the distances where we have constructive interference. So that's problem 1. Problem 3. I hope you guys, I know if you're watching it not live, that you have a piece of paper and you're going through these things and you're fixing the mistakes as I'm making them and going through these problems. Problem 3. Problem 3 is a sound wave, okay? It says, two speakers emitting identical sound waves of wavelength lambda equals to 2 meters. So problem 3. So in here, lambda is equal to 2 meters. That is given to us. Lambda is already given for this problem. In phase with each other, and observe it, and an observer located as shown. At the observer's location, what is the path difference for waves? So this is the sources. So we have S1 and S2. Here is S1, and here is S2. The distance between them is 6 meters. And then the observer is in here, and the difference between him and the source 2 is actually 8 meters, given that way. Obviously, we need to find this distance also, since this distance will be R1. And this distance, we need to use the Pythagorean theorem because this is a right angle triangle. And this is the square root of 8 squared plus 6 squared, and that is square root of 100, which is 10 meters actually. So this is R2. Okay, this is 8 squared, which is 64. And 36, 64 and 36 is 100. Square root of 100 is 10 meters. So the difference between S, oh man, I labeled them differently. That's fine. So this is S1, this is R1 and this is R2. The difference from S1 to the observer is R1. The difference from it doesn't matter. We're taking the difference in absolute value anyway, because again, the cost, the properties of the costs. Cause of property of the cost doesn't matter which one you call S1, which one you call S2. So we have two sorts of waves in this case, and an observer is a distance from M. From them, it says in here, question A, what is the path difference for waves? So the path difference in this case, delta, is just 10 minus 8, which is just 2 meters. And I took it in absolute value, okay? I didn't take R2 minus R1, or if you want to, you take R2 minus R1, and it's in absolute value still 2 meters. 8 minus 2, 10 is still 2 meters. The reason is, again, because of this property of the cosine. The cosine of k times R2 minus R1 divided by 2 is the same as cosine of k times R1 minus R2 divided by 2. And the reason being is cosine is an even function. So cosine of alpha is the same as cosine of negative alpha. That's why I take this in absolute value. I don't care which one comes first. As long as I take the big minus the small, that is fine, because you're dealing with a cosine function when it comes to the difference in paths. So this is how long more one will travel than the other. One will travel 10 meters, the other one travels 8 meters. So there is the difference in path of 2 meters. That's in a nutshell the answer to question A. Question B, will the sound wave interfere constructively or destructively at the location of the observer? Okay, lambda is 2 meters and delta is 2 meters. So as a matter of fact, delta is equal to lambda in this case. And as long as the path difference is any multiples of lambda, integer values of lambda, the interference in this time is going to be constructive. That's it. So it's a constructive interference because the path difference between them is lambda or any multiple of lambda, as long as it's m lambda, where m can be 0, plus or minus 1, plus or minus 2, and so on and so forth. In this case, it's plus 1. Had it been 0, it's the same thing. If he decides to sit right in the middle in here, there will be constructive interference too, because the path between S1 and S2 will be the same. That, in the case, is going to be 0. The path difference is going to be 0. So if, as he or she decides to move around, the path difference is going to change from values of 0, basically, so that there is no path difference whatsoever, to any value in between them. It could be half a lambda. If it is half a lambda, that is actually destructive interference. Half a wavelength is always destructive interference. Full wavelength is constructive interference. So that is the purpose of these two problems. Problem 1 and 3, we're really teaching you this idea. They are trying to emphasize the fact that constructive interference happens when there is the path difference is a full wavelength or multiples of it, integer times, including 0, or if it is a half integer of a wavelength, positive or negative, it doesn't matter which one comes first, as long as there is a delay of lambda over 2, then in this case it's destructive interference. And again, positive or negative has to do with the cosine function that you're dealing with. Now, it could be anywhere in between them, as a matter of fact. That's the point that I'm going to say too, because the cosine could have values between 0 and 1. Of course, when you square it, because the intensity has to do with the square of the cosine. Otherwise, the cosine can be from -1 to +1, but when you square it, it's only between 0 and 1. There is some intermediate values. So if you move along, the intensity actually does not abruptly go from 0 to full intensity. It's going to increase until some maximum value, and then it's going to decrease back to 0. So that is basically what this whole point is. As a matter of fact, part C, suppose the observer now increases her distance from the closest speaker to 17 meters, staying directly in front of the same speaker as initially. So she moves back, basically. So again, let's go back into S1 and S2, the two sources. This distance is the same, 6 meters. And she moves back, looking at this source in here. So this is the observer O. And keeping her distance, keeping her direction, so that this distance is actually 17 meters. So all we have to do now is use the Pythagorean theorem again and find this distance, that's all. And that is going to be square root of 17 squared plus 6 squared. And that is going to be square root of, open parentheses, 17 squared plus 6 squared. So it's 18.02. How many sig figs in this problem? It's 2 sig figs. So if it's 2 sig figs, it's 18 meters. Okay. So this distance is 6.0. This distance is 17 meters, and this distance then is 18 meters. Answer the questions of part A and B for this situation. Well, question A, it says the path difference in this case is going to be 18 minus 17, because one of them travels 18 meters, the other one travels 17 meters, and the path difference is exactly going to be 1.0 meters. And if you notice, this path difference is exactly 1/2 of 2.0 meters, and that is 1/2 of a wavelength, because the wavelength that was given in the problem is 2 meters. So this is a half wavelength. So this distance from here, she's not going to hear anything. So the interference in this case is going to be destructive interference. So for this part of the problem, I know Daniel just joined us, and the problems we're tackling, Daniel, are problems 1, 3, we just did 3, and 6, 9, 13, and 20 from this chapter, chapter 35, okay? So hopefully you come back at least to look at problem 1, because problem 1 and problem 3 are actually similar in a sense, we're trying to basically understand the idea behind constructive and destructive interference, okay? So in terms of wavelength, constructive interference is when the wavelength, the optical path is lambda. The difference between the optical paths is lambda, and it doesn't matter which way you take it. You usually take the bigger minus the smaller. And it's destructive when the optical path difference is going to be lambda over 2. So this is exactly how we found the first part of this problem. And now we're finding the second part. So the first part was constructive interference. This one is actually destructive interference. When she moved back 17 meters, now at that point, the wavelength, I mean, one source sends a signal, the other one sends a signal. One of them travels 18 meters to reach her, and the other one travels 17 meters to reach her. The difference in path is exactly 1 meter, which is half wavelength. If it's half wavelength, then in this case, it's it's destructive. End of the story. I know this problem is given in terms of sound because she would move a distance that is actually practical. You can move a meter, you can move 17 meters, you can be 8 meters. If they give us light, as the previous problem was, as problem 1 was, remember the wavelength in here, even for this one was not bad really, for radio waves, but radio waves, how are you going to see it? You cannot see it with your own eyes. Remember the spectrum in here, the radio waves, you have to really have a phone in there to capture it, okay? So it could be a cell phone, for example, sitting at different points in here, and when are you going to get your signal or lose signal? So that is something that you might experiment with. But in the case of cell phone, in the case even in the radio waves bounces off of different obstacles and come back to you. So there will be always constructive interference at some point. I mean, there will be interference at some point. So yes, as you move along, the signal improves or destroys, but this is not done in vacuum. So this experiment in here, you have to be careful with it. So you cannot really do that. Even this one, you have to be careful with it. Because as she moved back in here, this source is sending a signal, but it could be bouncing off of a different medium, and this one could be bouncing off, and then she could still hear the sound. So even if she moves 17 meters from here, where according to this picture, it's going to give you destructive interference, not quite if you do it in practice, because of the fact that there is sound bounces off of the floor, bounces off of different obstacles around here and there, and basically they become secondary sources, okay? So then you can still hear sound, okay? Anyway, so this is basically the idea behind it. The point being in here, if the path difference between the two sources is a full wavelength, it's lambda. I mean, it's a constructive interference. If it's 0 lambda, or 1 full lambda, or 2 full lambdas, or 3 full lambdas, it doesn't matter, plus or minus, then in this case it's constructive. If it is lambda over 2, positive or negative, if it is 3 lambda over 2, positive or negative, if it is 5 lambda over 2, positive or negative, you have destructive interference. So that's a summary of these two problems. Problem 6. Problem 6 says a coherent light of wavelength 500 nanometers. Now we're talking about stuff that is related to more closer to the chapter. Okay. I mean, not that the others are not, they are general, the other two problems. So problem 6, coherent light of wavelength lambda equals to 500 nanometers. So lambda is 500 nanometers. 500 nanometers is really probably the blue light. Okay, so this is visible. This is something we can see with our own eyes. Okay, is incident on 2 very narrow and closely spaced slits. So you have a slit in here. Actually, I'll do it backward. And another one in here. Okay, and the separation between them is small. The interference pattern is observed on a very tall screen that is 2 meters from the slits. So at the distance 2 meters from it, there is a very tall screen. Okay. So these are the openings, by the way, the sources. So there is an obstacle in here that you cannot see the light behind it. Otherwise, you have a problem. So the light can go only through these 2 openings, okay, to these 2 slits. And they're blocked from every other place in here, okay? Near the center of the screen, the separation between 2 adjacent interference maxima is 3.53 centimeters. So if I go to the center in here, we know the center is going to be bright. So this is bright. In other words, it's a maximum. Followed by minimum, followed by another bright, which is also a max. So somewhere in here between them, there is a min. As a matter of fact, there is one also on the bottom in here too, okay? And so on and so forth. So this is a max, followed by a min, then a max, and so on and so forth. There is a max in here too, and so on and so forth, okay? This is a central one. In here, the difference between these two paths, the distance in y, is given to be 3.53 centimeters, okay? So the delta between the maxes is this much. Let's put a max in here. In other words, y max 1, the first max, which is this one, and the central one, which is 0, is this number, is 3.53 centimeters, okay? So that's what the problem is saying. What is the distance between the 49th and the 50th maximum? So there is a maximum in here that is number 49, followed by another one that is 50. So we're counting 1, 2, 3, 4, 5, 6, all the way. We reached 49. Remember, they said that this screen is tall, so it's going to capture them all. Okay. So this distance at the end is not, it's going to be a big distance in here. So I cannot use the small approximation for this angle. So this is the theta 49, and this is the theta 50. I cannot say that tangent of theta 49 is very small so that its tangent is equal to its sine. This is not correct because 49 is a big number, most likely, okay? So I have to be careful in here. So this approximation is not going to work for us. But it's going to work for the immediate neighborhood near the bright. So for 1 and 2, it's going to be fine. And we know what that is. So what do we have in here? On one side, this is true all the time, always. D sine theta is equal to m lambda. This is for the bright. This is what we found from the chapter. So this theta in here for the bright, okay? In other words, for theta equals to 0, we know that m is equal to 0. For theta is equal to 1, we know that d theta of sine theta 1 is equal to, 1 times lambda. For theta equal to 0, m is equal to 0. That's the central bright fringe. That's true always. So this value in here, theta 1 is very small now, okay? So we can say theta 1 is roughly lambda over d. That's how much it's going to be, because theta 1 is equal to, in radians, okay? Because sine of theta 1 is roughly equal to theta 1. Tangent of theta 1 is roughly equal to theta 1 also. In other words, this is the tangent. The tangent of theta 1 should be equal to this distance, which is 3.53 divided by 2 meters. As a matter of fact, we know how much this tangent is. So tangent of theta 1 is equal to the first distance, which is actually this distance in here that was given to us, the delta y between the maxes, divided by the r, which is 2 meters. So this is r, how far the screen is. So now we have everything apparently to solve this problem. So we need actually, did we get the lambda? Yes, they gave us lambda. Lambda, they said it's 500 nanometers. Well, they didn't give us a separation d between them. We don't know how far they are. So we can use this equation to find what d is. So theta 1, and plug it into this expression, and it's going to give me the distance d. As a matter of fact, the distance d from these two equations is going to be d is equal to lambda over theta 1. Theta 1 has to be in radians. It cannot be in degrees if you're going to use this expression. And theta 1 in radians is roughly equal to delta y max divided by r. So from here, we have an expression for d, which is just lambda over the difference between them times the radius r. Let's make sure that everything is in the correct units, okay? This one was given in nanometers. This guy was given in meters. This guy was given in centimeters. So you have to be careful in here. If I convert one of these two to centimeters, and it's actually easier to convert the meters, because 2 meters is 200 centimeters, that cancels the units, and the answer is going to be in nanometers. So let's leave lambda alone, which is 500 nanometers. Convert R to meters, that's 200. Did I make a mistake in the calculation? So no, it's good. 200 centimeter, that's where R is, and divide that by delta Y max, which is 3.53 centimeters. That is basically all we have in this problem. So from here, we have a D, the separation between the slits. We need that separation. So let's do the math. We have 500 times 200, that's what? 10,000? No. That's 10,000, it's 100,000. So 500 times 200 divided by 3.53. In nanometers, okay? So this answer is 28,300 nanometers. We have 3 sig figs, so it's 28,000. Control Z. 28 times 28.3 times 10 to the power 3 nanometers, and 10 times 1,000 times nanometer is actually a micrometer. So this is 28.3 micrometers, or if you're careful with it, it's actually if I divide this one again by 1,000, so it's going to be 0.0283 millimeter. Okay. Or if you want to, it's 2.83 times 10 to the negative 5 meters, okay? So again, you have to remember the nano is 10 to the negative 9, and the micro is 10 to the negative 6, and the milli is 10 to the negative 3, and the meter, so this is milli, not meter, okay? This is micro, and that's a nano. So again, this is the distance between the slits. And it's small enough so that this phenomenon can be observed. So that's the whole point of this Young's experiment. Okay, so we have D. Now we need to find theta 1 and theta 2 and find their separation between them. I mean, not theta 1, theta 49 and theta 50. So we need to apply the same rule now, where it says that D sine of theta 49, that's the 49th maximum, is equal to 49 times lambda. From here, we're going to find theta sine of theta 49 as being 49 times lambda, and lambda is 500 nanometers, divided by, oh, that's good, that's good, that's good. Look, keep it as is, because you have D in nanometers, and you have the numerator in nanometers, so the nanometer cancels the nanometers, divided by D. In D, keep it in nanometers so that the nanometer cancels the nanometer. So I'm going to use 28.3. Is it 28.3? Yeah, 28.3 times 10 to the power 3 nanometers. That way, the nanometer cancels the nanometer, and the answer is going to be 49 times 500 divided by, open parentheses, 28.3. Oh, I have the answer actually, which is, I'm using the full value, okay? Not using the approximate value. So it's going to be 0.86485, and that is sine of theta 49. Now this is a big angle. As a matter of fact, since I'm using degrees in here, arc sine of this value. You have to be very careful in here, not to, it's actually 59 degrees, 59.86, 60 degrees. Theta 49 is roughly 60 degrees. That's a big angle. We cannot say sine theta 49 is equal to, that's a point I was making earlier. You cannot make this approximation now, because theta is actually almost 60 degrees. And let's find 50. It's the same thing, 50 times 500 nanometers divided by the same number, 28.3 times 10 to the power 3, and that's going to be a big number also. So again, it's going to be this number times it's actually 0.8825. So in other words, theta 50, I'm going to use the arc sign. Hopefully you guys are doing all of this. You're not just watching me do these things. And if I make a mistake, hopefully you catch it. Because again, so it's 61.9 or 62, roughly 62 degrees. Okay, both of these angles are big angles as expected. Are big angles, and I cannot say that their tangent is the same as their sine. That's not going to work. And we're supposed to find the distance, actually, y of 50, and y of 50 is equal to r times tangent of 50, theta 50. And also y of 49, which is equal to r times tangent of theta 49. Let me see where that is coming from. We're looking at this distance, basically. How far is theta 49 on this axis? That is what y of 49, I'm sorry, is right now. So it's this distance. From this geometry, this is r, and this is theta 49. We just found it. The tangent of theta 49 is equal to y 49 divided by r. And the tangent of theta 50, which is this angle, is actually y of 50 divided by r. So that's the formula I'm using. So I need to find y 49, and I need to find y of 50 and find how far apart they are. It's not going to be 3.53 centimeters. This is valid only near the center. This distance should be slightly bigger, because as you move up in the axis, the bright slit starts to space out a little. So let's find that distance now between them. So we need to use this thing in here. Okay, there are two ways of doing this one. Remember, sine squared plus cosine squared is equal to 1. So all I have to do is just divide by sine squared in here. So this will give me 1 over sine squared is equal to 1 plus 1 over 10 squared. And in here, I can solve for 1 over 10 squared is equal to 1 over sine squared minus 1. Invert this entire expression, gives me tangent of theta is equal to 1 over the square root of the inverse of this number, which is 1 over sine squared minus 1. And plug in, since I know what the sines are, which are these values actually, sine of theta. Wait a minute. Yeah, this is the sine itself. Okay, I divided already by d in here. Okay, d is divided 4, so this is sine of 50, and you plug in here. You invert this number and you square it, and you subtract from it 1. And you invert it, or you just use the values that we just found for theta 1 and theta for theta 49 and theta 50. Theta 49 is roughly 60. I'm going to use the exact number, which was 59.8655, whatever that number is. So hopefully you guys have a calculator and you're doing the same thing. So I'm going to multiply r, which is 2 meters, times the tangent of this angle, and this angle is this one. So that is for 49 actually. So theta 49 is 3.445 meters. So this one is 3.4454 meters. I'm keeping some significant numbers in here because I don't know what the other value is, because I need to find the distance between them. And the other one is actually 2 times the tangent of the 61.9, actually not full 62 degrees. And the tangent of the distance for this one is 3.75. I should probably have kept this much, but that's fine. 282 meters. And now the difference between them, which is exactly what we're supposed to find, the Y50 minus Y49 is going to be the bigger number, because it's bigger, okay? It has to be bigger because it should be separated, it should be on top, minus the first one. Come on. I'm not going to make it, so forth. Okay. It's 30 centimeters. 0.307 meters, or 30.7 centimeters. See the difference between them? The first few of them immediately next to the central fringe are separated by 3 centimeters away from each other. As you move along up in here, the separation starts to increase until almost 10 times when you are reaching 49 and 50. Remember, the whole problem in here, they give you a very long screen so that you capture as many as possible. At least you need to capture to the 50th brightest G, but it's going to be too faint to be seen. You really need to have a sensitive equipment to see it, but it's there, okay? But there is a bright spot in there. So that is how far it's going to be. It's going to be 3.75 centimeters, 375 centimeters, almost 4 meters away from the central point in here. So you have to have at least 8 meters long screen. That's a big screen. That's like a wall. Okay, it's not a. I mean, if you consider that it's only from the bottom and you put the experiment from the bottom and you ignore from the, it's at least you need about 4 meters high. That is actually a tall wall. You really need to find this one because 3.75 is almost 4 meters for the 50 centimeter. The other one is a little less than 3.5 meters, 3.44 meters. So that is how high these bright fringes are. Of course, in this case, there is no way you can tell me that sine theta is equal to 10 theta. It's true only for the small angles near the bright fringe, near the central bright fringe. Okay. Does this problem make sense to you guys? Just the physics, forget about the math for right now. Yes, no? Maybe? Okay, very good. So here is the deal. The math follows from only this relationship, really. And where M is 0 for the central bright fringe, is 1 for the next one, and then also it's 49 for the 49th bright fringe, and 50 for the 50th bright fringe. So this relationship, we used it extensively. The other relationship that I used it, and I used it in its approximate form and its full form, is basically the tangent of theta, the same theta, by the way, is y over r. We used it in the case where we are very close from the center, where the sine and the tangent and the theta itself in radians is the same. So in this case, the sine theta and the tangent theta are the same. So we used it to find basically d, because we need d for our calculations in here, for the 49th and the 50th. After we find d, then we found the theta 49 and theta 50 using this expression, since we know what d is now, and m is 49 and the other m is 50, and lambda is given 500 nanometers. From here, we can find the two angles, theta 49 and theta 50. The 49th bright fringe, how much angle you need for it, it turns out to be about 60 degrees, and the 50th turned out to be about 62 degrees. Then we went back to this expression and find the y's for them on the screen. Because we have found theta, the two thetas, then we found the difference. So that's basically in a nutshell what this problem is. I know the numbers, sometimes they make it a little bit confusing, but that's basically in a nutshell what this problem is. Okay, problem 6. Problem 9, as a matter of fact, problem 9 is similar. Problem 9 says two slits spaced 0.45 millimeter away. So basically they gave us D in this case. So this is problem 9, okay? So they gave us D to be 0.45 millimeter. They made sure that we're dealing with 3 seg figs in this problem too, okay? Actually for 450 millimeters, 0.450 millimeters. And they are placed distance between them and the screen of 75 centimeters. So in other words, R is 0.75 meters, okay? So they gave us R from a screen. What is the distance between the second and the third dark fringe, dark lines of the interference pattern and this? So and they gave us the wavelength lambda to be 500 nanometers. And here we need to find, what is it? The second and the third dark fringes. Second and third. Dark fringes obey a law that is slightly different. It says D sine theta are equal to M plus 1/2 times lambda. That's all. We have lambda, we have D, and we need to figure out what M need to be. So for M equals to 0, that is the first. We don't need the first, we need the second. And that is M equals to 1, the second. Okay? For M equals to 3, that is the third. No, M is equal to 2, I'm sorry, that is the third. Okay? Because M can be 0, plus or minus 1, plus or minus 2, and so on and so forth. Okay? So we need to find them. 0 is immediately, so this is a bright, and then this is dark here, followed by bright, followed by dark, followed by bright, followed by dark. So this one is not. They said between the second, here is the second, and here is the third. We need to find this distance between them. Okay? So that's all there is to it. So we need to find the theta for second, and we need to find the theta for the third, and then use the relationship again that tangent of the thetas is always given by y over r. So then we will find the y for the second and the y for the third, and then take the difference between them. That is the answer that we're supposed to find. So let's find the theta for the second. So we're going to second. So that corresponds to M equals to 1, by the way. 1 plus 1/2, that's 3/2 lambda divided by D. So it's going to be the arc sine of 3/2 of lambda divided by D. 3/2 of lambda divided by D. Okay. Well, lambda is 500 nanometers and D is 0.45 millimeter. I need to convert things to correct units, okay? Otherwise, we have a problem. So the nanometer can be written as 10 to the negative 6 millimeter. Okay, that's it, because it's a millionth of that, and we're done. So we don't need to convert into meters or anything. Or if you want to, you can write this one as 10 to the negative 3 meters, and this one 10 to the negative 9 meters, just to make sure. So it's arc sine of 3 times lambda, 500 nanometers, divided by 2 times D, which is 0.45, times 10 to the negative 3, because it's in millimeters. That's the negative 6, if you wish, okay? Now, 2 zeros in here cancel some of the zeros in here. I have negative 4 left in here, so that I'm dealing with 15 over 2 times 0.49. So 15, oh no, I have to use the arc. Arc sine of 15 divided by open parentheses. We should really be careful here, because we have that 10 to the negative 4, okay? I don't want to ignore that. So first of all, 15 times 10 to the negative 4, open parentheses, again, divided by open parentheses, which is 2 times 0.49 or 0.9, actually. Okay, close to the two parentheses. And the answer is 0.0954 degrees, or 0. So this is what this is saying in here. It's 0.0955 degrees according to my calculator. This is a very tiny number. This is a very small number. Okay. As a matter of fact, its sine, because we need its tangent. Its tangent is going to be this much. So the tangent is a very tiny number, 0.01666666, something like this, repeating. So in other words, what I need really is I need the y for the second. The y for the second is going to be equal to r times the tangent of this angle, the tangent of the arc of the sine of 3 lambda over 2d. So that is basically the expression that I'm looking at. So this y should be it's so small number, 0.00. Let me multiply it by because this is in meters actually. Let me multiply it by 100 just to get it in centimeters. Okay, so it's not even a full, not even a, so 0.125 millimeter. Okay, well, that's how far it is. It's not too far. Okay, because the distance is actually small. R is 75 centimeters. So now we need to find the y third. It's going to be the same formula, except that the number in here, when you place 2, it's going to be 5 halves. 2 plus 1 half is 5 halves. So this number 3 becomes 5. So it's going to be 5 lambda over 2d. So it's going to be the same expression as before. So which is going to be 75 centimeters times. So the answer is going to be 75 centimeters. Okay. So it's going to be 75 centimeters times the tangent of the arc sine of 5 times 5. So don't forget we have lambda, which is 5 also. 500 times 10 to the negative 4 divided by, open parentheses, 2 times 0.45. Close parentheses, close this parentheses. And the answer is 0.208 millimeter. Okay, because I'm sorry, this is centimeter. This is centimeter. This is centimeter because I used R 75 centimeters. Please verify all of these things, okay? So the answer is going to be in centimeters, okay? So we're doing minus the first distance. So it's 0.083 centimeters. The difference, y third minus y second, is 0.0833 centimeters. Okay, it's very tiny. That's the point in here. Please verify all of these numbers. Okay, I used R at the end, 75 centimeters. I didn't choose 0.75 centimeters, 0.575 meters. Okay, so that's why the answer should be in centimeters, not in millimeters. I mean, I meant to say 1.25 millimeters, and this one would be 2.08 millimeter. And obviously, the difference between them is going to be a fraction of a millimeter. If we do it that way, now it's a fraction of a centimeter. Okay, so that's problem. Still have about 10 minutes, so let's discuss the remaining of the two problems. Okay, problem 13, which is the next problem. Problem 13, it says 2 very narrow slits are spaced 1.8 micrometer. So they gave us D to be 1.8 micrometer in here. And apart and place 35 centimeters from the screen. Now they gave us R to be 35 centimeters, which is even smaller than the second problem, okay, the previous problem. And they tell us what is the distance between the first and the second dark lines of the interference patterns when the slits are illuminated with a lambda that is 550 nanometers. Okay, so now we have to be careful in here. 550 nanometers. Okay, that's what lambda is. And they want to find the distance between the first and the second. Here is the trouble with this problem. You're supposed to find the y's in this case. But before you do that, you need to find the d's. The d in this problem is equal to, for the dark fringes, between the first and the second. So m is equal to 0, and m is equal to 1. And the formula is the same as before. D sine of theta is equal to m plus 1/2. These are dark fringes times lambda, okay? So we can find the two thetas and use this formula. Here's the trouble with this problem. D is a very small number, 550 nanometers. That's true. I mean, lambda. And D is also a small number, 1.8 micrometers. This is a very small number now. You're dealing with a very tiny number. So these thetas are not necessarily small. That's all. So we really have to use the same formula as the previous problem. Do not make the approximation. And it's identical to the previous problem. With the only exception is the previous problem we're dealing with m equal to 2 and m equals to 3. This one deals with m equals to 0 and m equals to 1, and that's it. So this problem is similar to the previous problem, and do not, like I did in here, I did not make the approximation, but if I did the approximation, it's going to be 100% justified. So theta in here is in such a way that the tan theta is approximately equal to sine of theta. Here, it's not going to work because of this d being so small. Okay, so lambda over d is not going to be necessarily a small number, because had d been big like the previous problem gave you a d that is 0.45 millimeter versus 1.8 micrometer. So the d now is much significantly smaller than the previous d, therefore, which makes this theta as big. So in this case, I cannot probably say that tangent of theta equals to sine of theta. Having said that, the calculation is identical, because even in the previous problem, I didn't take advantage of this approximation. I just calculated the tangent, end of the story, and the answer was very close from the same. Actually, if I did the approximation, I would have found the same answer as in here. But in here, you cannot. You have to proceed exactly as the previous problem, okay? With the exception that m is equal to 0 and m equals to 1 in this case, versus m equals to 2 and m equals to 3 in the previous problem. That's it. Okay, so that's problem 13. Problem 20, we get the time. For problem 20, it says you have two slits spaced 0.0720 millimeter apart. So they gave us D in here. Okay. And R 80 centimeters from the screen. So they gave us R to be 0.800 meters. Okay. The extra 2 zeros are just for the sig figs. Coherent light of wavelength lambda passes through the two slits. So lambda, they didn't give us what lambda is. The two slits. In their interference pattern on the screen, the distance from the center of the central maximum to the first maximum is 3 millimeter. So again, similar to the first problem, or one of the previous problems, they gave us a distance between the central bright fringe and the first bright fringe. This distance is 3 millimeters. This delta y is 3 millimeters. Again, they made sure that it's 3.00 to make sure that you take 3 sig figs. The intensity at the peak of the center is 0.0600 watts. So I naught is equal to 0.0600 watts per square meter. So they gave us what the central intensity, what is the intensity at the points on the screen given by 2 millimeter, 1.5 millimeter of the central bright fringe. So they want to know the intensity here and the intensity here, midway. So this distance is 3. They wanted to know 1.5 millimeter, which is supposed to be 0-ish, I suppose. And then the intensity in here, which is somewhere 2 millimeter. So they want to know this intensities. So the first thing we need to do is find this lambda. Once we find lambda, we're in business. Okay? So we know that the first bright fringe, we have its y, we have its r. This distance is 80 centimeters, and this is the y 3 millimeters. So we know what theta 1 is. Tangent of theta 1 is equal to this delta y, if you wish, which is y1 divided by r, and y1 is given. Y1 is 3 millimeter divided by r, and r is given to be 0.8. From here, we can find what theta 1 is. So assume that we can do the algebra in here. Okay? If we find what theta 1 is, we can find what the lambda is, because m is equal to 1 for the first bright fringe. Okay? So in this expression, since we know what this tangent of theta 1 in here, I can do the arc10, plug in here, I can find what lambda is. So assume that we can find what lambda is from this expression. We're in business. Okay? Everybody's good now. So we have found what theta 1 is. Based on that, we're going to find what the actual lambda, since it was not given to us. From here, we should be able to find the intensities anywhere else in here. Here is the deal. I want to find this angle theta in here, which is some angle in here for this distance. Well, this angle from here is given by arc tangent of this distance, which is 2 millimeters. So I'm going to call it y in general, y divided by r. So we have the theta for that one. Since we have the theta for that one, I can find the path difference between the two waves. Okay, here is the deal. The first one left this point and met in that point in here, and one of them travels a distance delta, which is r2 minus r1, greater versus this distance d in here, so that delta from this right angle triangle is again equal to sine of theta times delta. D is equal to delta, the path difference. Okay. Now the phase with which they will arrive is going to be k times this number divided by 2. Remember the phase difference that we have found. In this case, phi is going to be this delta, this k times delta. And k is 2 pi over lambda times delta. And delta is just d sine theta. So this is the path difference, how much, I mean, the angle in terms of how much difference they are. This is what we use actually in the formula. Well, in this expression, we have everything. We have theta that we can find from arctangent of 2 over r. R is given, and the 2 is given, 2 millimeter, and r is 80 centimeters. So convert things, and you have theta. You have d that was given. You have lambda that you calculated, so you can find the phase in here. And you use it in the intensity expression that we have found, which is I naught times cosine squared of this angle divided by 2. And this angle divided by 2, the 2 cancel the 2, is going to be I naught cosine squared of pi times d times sine of theta divided by 2. That's all. I mean the lambda divided by lambda, because the 2 cancels in here, this 2 and that 2 cancels. We have theta that we can calculate. We have d that we can, it's given. We have lambda that we calculated. And we have I naught that was given, the central by fringe. So we should be able to find the value for I in watts per meter squared. And the same thing for the other distance. Okay, we're going to plug in everything in here and we multiply it by that, because for that we have different y. Once we have a different y, we can find a different theta, which we'll plug in into this expression, and we're done. Okay, so we have 1 minute left. I'm going to leave it to you guys to finish this problem, and if you have difficulty with it, please communicate with me. Okay, so I'm not going to leave it completely up to you. I really want to make sure that you guys understand how to do this kind of problems. Sounds good? Okay, very good. So I'm going to stop sharing the recording.